So we're going to find the fourth roots of 81i, which plots itself here, right up on the imaginary axis. That gives you a theta of 90 degrees or pi over 2. The radial distance is 81. We're going to fill in this formula. Z sub k equals the nth root of r times cosine of theta plus 360k over n plus I times the sine of theta plus 360k over n. What values of k should I run through? Zero, 1, 2, and up to n minus 1, which is 3. Perfect, thank you. Let's fill in some things here. That's going to be the fourth root of 81. Cosine of 90 plus 360 times k over n, which is 4, plus I times the sine of 90 plus 360k over 4 again. And so that's our general formula. Let's start plugging in specific values. Z sub 0. If I put in a 0 for k, then I'll end up with the fourth root of 81. Well, does anyone know what the fourth root of 81 is? Or how to find that fourth root? I'll help you out. So you go back to the math menu. Let's see if my calculator works. It is 3, yes. So I guess I have to do it kind of manually because SmartView seems to be stuck. But yes, if you hit the math key and then the fifth option down, allows you to do, let's say, the fourth root of 81. And that's 3. So we'll just put a 3 out in front. Cosine of 90 over 4. 90 over 4 is 22.5. Plus I times the sine of 22.5. Okay, beautiful. Let's take a look at z sub 1. Again, up front I'm going to have a 3. This time it's going to be cosine of 90 plus 360. That's going to be 450. 450 divided by 4. I think that's going to be 112 or something like that. Let's see, 450. I don't know why this is dead. I'm just going to have to kill this one. All right, so 450 divided by 4. Yeah, 112.5. Thank you. 112.5 plus I times the sine of 112.5. And so on. We got to keep going. If you plug in a k equal 2, 2 times 360 is 720, plus 90 is 810. 810 divided by 4 is going to be 202.5. Plus I times the sine of 202.5. And the last one, if you plug in a 3 here, we'll end up with 3 times the cosine of 292.5 plus I times the sine of 292.5. The unfortunate thing about working in degrees as opposed to radians is that if I wanted to write it in exponential form, that is r e to the I theta, I couldn't. You have to have this written in radians in order to do that. So if you needed to, if you wanted to turn this into something that had radians, you could just take one of your angles. Let's just do the last one. and I'm going to take 292.5 times pi. So times pi divided by 180. And there it is in radians. So 5.105. So it'd be 3 times cosine of 5.105 plus I times the sine of 5.105 in radians. Now that I've got it like this, now I can easily turn this into exponential form. That would be 3, oops, that was weird, lamp. There we go. 3 times the cosine, or 3 times e to the I times 5.105. There's your exponential form. The advantage of this is that if you have it in exponential form, it can make it easy to give it in x plus yi form on your calculator. To do that, if you needed that, then I would do this. Go to your mode key. Go down to this line that says real right here. And let me zoom in a little bit more. Go over to a plus bi. Press enter on that. Then you can exit out of here. Second quit. If I now type in 3 and then e to the I is down here, second I, times 5.105, then it should give me my a plus bi. What's wrong there? 3, oh, I'm in degrees. I should be in radians. Let's see, math, mode. There we go. There we go. See, you do have to be in radians. It won't work in degrees. But there's your A, and there's your B times I. Beautiful. All right, those are pretty challenging. So do spend some time practicing this because there's a lot to it, and it's, you know, kind of a heavily weighted problem on an exam. Comments or thoughts on that one? Probably degrees. But, I mean, I could ask either one, but probably degrees. Let's take a look back at some more examples here. Let's see. Go away, go away. Update. It's if you try doing this in degrees, 3 times cosine and then 3 times the sine, you could do that in degrees and you would end up with the same thing that I got on my calculator just a minute ago. Yeah. Now this is just the last of these. It's just Z3 in radians. That's all I did was put Z3 in radians here. That's okay. Nothing wrong with that. I just haven't done it in radians. That would be, you know, a little bit more work to go back and do it in radians. I think the easiest thing at this point would be to convert these angles directly to radians. That'd probably be the easiest thing to do. Okay, let me reload this and go back to one of the old exams. We're going to look at the answer key. Now I would suggest that you actually look at the blank part of this first, and then then look at the answer key. Try and solve these problems. So 8, 9, 12, 13. So 8, 9, and 13 through 17. Those are all good problems. The one that I haven't touched on, that I can touch on, that's kind of cool, is this one, these polar graphs. I don't think I'm going to try and cram this in for you right now in terms of making a test question, but it is kind of cool. If you did r equals sine of n theta, let me add in a slider for n. 1, 2, here. At n equal different values, you're going to get some pretty neat graphs. Let me see. Let me try and make these step by 1 and up to 8. So when n equals 2, sine of 2 theta, you've got this nice 4-leaf clover. If n equals 3, all of a sudden I go down to a 3-leaf clover. But at 4, now I've got 8. At 5, I've got 5. At 6, I've got 12. At 7, I've got 7. How many do you think I would have at 8? How many petals do you think I would have? Have you spotted the pattern yet? 16. So the pattern is, for an even number, you get twice as many petals as n. For an odd number, you get the same. Yeah, so that's it. That was really the point of this problem on my old exam, was just asking you to figure out how many petals there would be. So I gave you one even and one odd number to deal with. Write the equivalent numbers in polar coordinates with r is greater than 0 and theta is between negative 360 and negative 360 and 0. So let's start out by looking at the point 5 and 130 degrees and figure out where that would be. So let's open up the unit circle and let me zoom out a little bit. There. And I'll move you out of the way. So the point 5 and 130 degrees. Well, let's see, maybe I can, do I have, yeah, here we go. This is the one I want. So 5 and 130 degrees, we could put a little spot on there. It's probably going to be out here someplace. About there. But instead of getting there with a positive angle, I want a negative angle. I want to go this way. So how would I figure that out? What would I do to go a negative direction? I want to do r and theta. I need to have 5, but what's theta going to be if I'm going in the opposite direction? Not quite, because if I subtracted 180, that would put me over here at some negative angle. Like negative 50. So it kind of pointing in the right direction, but it'd be in the wrong quadrant. Anyone else want to give that a try? Well, it's 130 degrees is not exactly one of our special angles. I just kind of estimated that it was here. But it's not one of your special angles, so it's not going to be like negative 7 pi over 4 or something like that. Yeah, 130 minus 360. So if I subtracted 360 from this, so let me come up with a different color. If I subtract 360 from this, I'm still going to be at an equivalent angle because 360 is just going to be once around the unit circle, but by subtracting 360, I'll end up with negative 230. And that's an angle that satisfies my requirements. I was looking for something with a negative angle and a positive radius, so there you go. You can play that same game with a negative radius and a positive angle. You remember what happens when you're dealing with a negative radius? What happens when you deal with a negative radius? When you're plotting things? Yeah. So if you're dealing with a negative radius, then the point that I want to end up with has to be on the other side here. So about here, thinking about here. So let's see, we wanted a negative radius and a positive angle. So here's my positive angle. It takes me to here. And then when I account for the negative radius, I'll go over here. The question is, what is that angle? So through here. Let's keep consistent. We're working in degrees here, so what would you do if you're working in degrees? What would you do? We want to get to 130 from 310. Well, what's halfway around the circle from 130? Yeah. So you're at 130. If you add 180, you get 310. 310 would be down here. All right, so those are kind of cutesy problems. I like them. I would expect something like that. Let's go back to, let's see, let's get rid of that. Let's go back here. Here's another one like that. This time it's asking you for a number between 360 and 720. So you can take your 130 and add 360. That's how you would get the 490. These I talked about earlier. So what makes it a cardioid? Well, it makes it a cardioid if these two numbers are the same. So 1729 and 1729. By the way, that's a famous number in mathematics. It's called a taxicab number. And I'll let you look that up at your leisure. This one, if the leading coefficient here is, or the leading number is smaller than this one, that's going to give you a limacon with an inner loop. If this number is bigger than this one, then you're going to get a limacon without an inner loop, which is going to look like this. The last one, this one is bigger than this one, so again, a limacon without an inner loop. So I'd probably give you something like this and ask that you work your way through this. I'll probably give you big numbers like this so that you can't easily graph these things. Now what we've missed out on, here's one. Convert between polar and rectangular coordinates. So this is going to start out in polar coordinates. You multiply both sides by this denominator. That gives you this equation. And then slowly but surely you're going to solve for r. And eventually you'll get down to something like this. Trying to think what the graph of that would look like. I guess it'd be a parabola. Yeah, it'd be a parabola in y squared, so it would face to the right. That much you're not responsible for. Another conversion problem, this time converting points. Another conversion problem, this time it's an equation. Problem 10 and 11 aren't going to be on our test, but graphing some points definitely will be. We practiced some of those. Trying to think of some of the questions that we just covered today. Complex numbers. You should be able to write it in any of these forms. So the first one's rectangular, then polar, then exponential. Let me make that a little bit bigger. There we go. Multiplying complex numbers, we practiced that. You got one practice, which was this one. Here's another one with answers you can practice. You need to start by putting these numbers in polar form first. Once you got them in polar form, when you're multiplying the numbers, you multiply the radius and you add the angles. If you've got this form, then this one, exponential form, comes pretty automatic. Square root of 4 or 4 square roots of 2 is pretty easy, and then the angle just goes up here. Raising something to a power. I'll probably do it like this. I'll probably give you an angle or a complex number that's already in polar form. That way you can show me you know how to use this formula. I will want it in x plus yi form when you're all done. So that is when you're done, you can convert it back. Let me see if I've got the example that we did earlier today handy. Yeah. So we're asked to find the fourth power of these, and it turned into something like this. Negative 128 times the square root of 3 plus 128i. Beautiful. If you were to write it in exponential form, it would look like this. So you got both of them. You got rectangular form and exponential form. I'd be ready for that. And of course, we just finished practicing one like this. There was Heron's formula. That comes from an earlier test. You might do well to look back at exam 2 and see if you can't find an example of Heron's formula. Let's take a look at exam 2. No, don't need those, nor those. That's probably giving you bad memories here. There's no Heron's formula on this one. There should be. Establish identity, exact angle, F angle. No, I'm not seeing Heron's formula on this one. So, but Heron's formula, that was for finding the area of a triangle. All right, and there was two versions of Heron's formula, or there's two versions of the area formula. One is Heron's formula, which is this one right here, and the other one was 1/2 of a times b times sine of the angle in between, and I'm not seeing that form here. So let me write it down for you, and then we'll call it a night. A, B, theta. If you wanted to find the area of this, it's enough to calculate 1/2 a times b times sine of theta. Theta is the angle between those two. We proved this one in class. Generally speaking, I give one problem that if you know this formula, you'll be in good shape. And the other one that I'll give is going to ask that you know Heron's formula, which is going to start out with S is 1/2 of the distance all the way around. And then the area is this formula. Square root of S times S minus A times S minus B times S minus C. Okay, I think you should be in good shape. Good luck. If you have any questions, please reach out. Otherwise, I will see you in class next week for the exam. Any final thoughts?